We're going to start by solving this logarithmic equation that has a single logarithm in it, and then we're going to move on to some that have multiple logarithms in it. Let's go ahead and start with this one. So I've got log base 2 of 3x minus 1 equals 3. I'm going to use the property that says log base a of x equals y can be rewritten. A is my base, y is my exponent, a to the y is equal to x. Let's go ahead and apply that property here. So for this one, my base is equal to 2. My exponent is 3, and I go ahead and write what's inside the logarithm on the other side, and that's 3x minus 1. Let's keep solving. I get 8, that's 2 cubed, is equal to 3x minus 1. Let's add a 1 to both sides. We get 9 is equal to 3x. I'm almost there. I divide everybody by 3, and I get x is equal to 3. Now, this is my answer, and it does work, but logarithms have domain restrictions. If I look at the graph of a generic logarithm, it looks like this. This is just log base a of x. So I need to make sure that whatever I've got for my answer works in my original logarithm. If I put a 3 inside here, 3 times 3 minus 1 is equal to 9 minus 1, which is equal to 8. I need to make sure that whatever my solution is, it keeps that argument of the logarithm, the thing inside the logarithm, greater than 0. And this one does, so I can go ahead and use it as my solution. So a few things to think through. Let's look at an example with 2 logarithms. In this one, I've got 2 different logarithms. I need to combine those into a single logarithm. So we're going to go ahead and use some of our log properties. I also have this 2 out in front here. So I need to apply 2 of my log properties. One of them says that log base a of x to the n is equal to n log base a of x. So this one says that I can bring my power out in front, or vice versa. We're going to use that for the 2 out in front. The second property that I need is for a sum of logarithms. So if I have log base a of x plus log base a of y, I can condense this. This is equal to a single logarithm of the product. So log base a, and I'm going to multiply what's inside together. So log base a of x times y. Let's go ahead and apply these to our problem. So we're going to leave that log base 8 of 2, nothing to simplify yet. Next, we're going to bring that 2 inside the logarithm as a power of what's inside. So this becomes log base 8 of that 2 to the x all squared equals 1. Next, I've applied this first property. Next, I'm going to apply the second property. I've got the logarithm of a sum. I can rewrite that as a single logarithm of their product. So I'm going to condense this into a single log. So this is log base 8. Inside, I'm going to go ahead and multiply the 2 times the 2x squared. So I get 2 times 2x squared. We're going to do some simplifying there, equals 1. Okay, well, 2x squared is 4x squared. So I get 2 times 4x squared. So what I've got inside there, I can write as log base 8 of 8x squared is equal to 1. Now I can rewrite this using the definition of a logarithm. 8 is my base, so I'm going to write this as 8 to the 1 is my power, so 8 to the 1 is equal to what we've got inside, 8x squared. As I continue to solve this, let's move it over here. Let's divide everybody by an 8. If I can squish that in there. So I get 1 is equal to x squared, and then I'm going to take a square root, so x could be either positive or negative 1. These are my possible answers. I need to check these next. So I need to make sure, and I only have one logarithm up here that has an x inside. I need to make sure that this stays greater than 0. Okay, so let's go ahead and put negative 1 in. It's not going to work, right? So 2 x, 2 times negative 1, is not equal to 0. So as I look at those two solutions, I have a negative 1 and a positive 1. Negative 1 is not going to work. It makes inside of my original logarithm negative. But if I try the positive 1, I am good to go. 2 times positive 1 is greater than 0. I can keep that one. So I'm checking each of my answers to make sure that it doesn't change any of the arguments, anything inside the original logs, less than 0 or equal to 0. Let's do another example. So in this one, I've got 3 logarithms. I've got log base 6 of x plus 1 minus, we're going to use another property there, log base 6 of x equals log base 6 of 29. So I'm going to apply this property. So this property says the log of a quotient, x divided by y, is equal to the difference of logarithms. That's going to work great for us. Log base a of the numerator minus log base a of the denominator. So what we have is the right-hand side of that property. So I can go ahead and combine my logarithms into a single logarithm, log base 6, with a fraction inside. My numerator is going to be the first expression, so that's going to be x plus 1 in the numerator. My denominator is the second one, that's going to be an x, and this is all equal to log base 6 of 29. Now on this one works really nice. Notice that I've got the same log base 6. Since I'm applying the same log base 6 on either side, it means that whatever's on the inside has to be equal. So I can go ahead and take what is on the inside and set those to equal. And all that matters is that these are a log of the same base. So I've got those isolated and I'm ready to just say, well, then the arguments, what's inside has got to be the same. Let's go ahead and cross multiply to solve this. I'm going to multiply by x, so I get x plus 1 is equal to 29x. I'm going to subtract an x from both sides, and I'm just about to my answer here. I have 1 is equal to 28x. Divide by 28, divide by 28, and x is equal to 1/28. Now I'm going to do a really quick check. I need to make sure that my arguments here stay greater than 0, and this one stays greater than 0. Well, when x is equal to 1/28, the argument of the second log is greater than 0. That's perfect. And for the first one, it's going to be x plus 1. So that's 1/28 plus 1, which is definitely greater than 0. So both of those work. And for this third one, it's just a 29, nothing to check with my x. So I've got my solution here. My answer is 1/28. Let's do one more. In this next one, we are going to need to solve a quadratic. So in this one, I've got 2 logarithms, and I notice that I have a sum, but they are both a log base 5. So I can go ahead and combine them using our property log base a of x plus log base a of y is equal to a single logarithm, so log base a of their product, x times y. Let's go ahead and do that on the left-hand side of our equation. So I can rewrite this as a single logarithm, log base 5 of their product, x plus 2 from the first logarithm, and then that x plus 1 from the second logarithm. I'm going to end up foiling here, just leaving the 1 on the other side, nothing to do there. So I end up with a log base 5. Let's go ahead and FOIL that. I get x times x, which is x squared. My inner is 2x. My outer is a 1x, so that's plus 3x. And then on the end, 1 times 2 is 2, is equal to 1. Now that I've got a single logarithm on one side and a number on the other, I can use the definition of the logarithm and rewrite this without the log. So I know that 5 is my base, so 5. 1 is my power, 5 to the first is equal to the argument, what's inside the logarithm, x squared plus 3x plus 2. I have a quadratic, so I need to get 0 on one side and solve using one of my strategies for solving quadratics. Let's subtract that 5. So I'm going to subtract that 5, and I get 0 is equal to x squared plus 3x minus 3. Now, I would love it if this thing factored, right? That would be so great. I would have an x and an x, but the only way to multiply to be a 3 on the end is a 3 times a 1. Maybe one's negative, one's positive. I'm never going to get to the 3 in the middle. Instead, I'm going to use the quadratic formula. Let me make myself a little bit more room, and we'll use that quadratic formula. Okay, so here's where we were. What we need to apply is the quadratic formula. So the formula looks like this. So x is equal to the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. So as I run through this, a is that lead coefficient 1, b is equal to the middle coefficient 3, and c is our constant -3. Let's go ahead and put this into the quadratic formula. X is equal to the opposite of b, so that's the opposite of 3, plus or minus the square root of b squared, 3 squared, minus 4 times a times c, all divided by 2 times a. Okay, so we are almost there. I just need to simplify what's inside that square root. Let's actually look at it over here. So I've got 3 squared, which is 9, minus 4 times -3, so that's going to be plus 12, and we get 21. 21 is not a perfect square, and it's 7 times 3, so no perfect square divides into it. So I can't simplify this any further. And then this is all divided by 2. So I really have two solutions here. One is -3 plus the square root of 21 divided by 2. That's one possible solution. And then -3 minus radical 21 all divided by 2. That's another possible solution. I want to check both of these. So I already put these into my calculator. It's so much easier to check a decimal to see if it makes one of my original logs 0. Let's see. So the plus 1 is 0.79. And the second one with a negative sign in the middle is about -3.79. Let's go ahead and do our domain check. I want to make sure that these possible solutions keep the argument what's inside my logs greater than 0, with both of them greater than 0. Let's check the 0.79 first. So that's going to be 0.79 plus 2, definitely greater than 0, and then 0.79 plus 1, also definitely greater than 0. So I can keep 0.79 as a solution, which actually I want to put a square around that one, my exact solution. Next, let's check -0.379. Okay, so it doesn't take long. So -3.79 plus 2 already fails. That is not greater than 0. So that means that I cannot use the negative part of my quadratic formula answer for a solution, and I've got one solution here. You are doing so great. Take a look at this next video, and thanks so much for watching.